Welcome back, AP Statistics. This is Chapter 12. We are almost halfway through the chapters this year. That is very exciting. So here we go.
Let's talk about observational studies to begin. In an observational study, researchers do not assign subjects to groups or alter any variables. Subjects are simply observed. So, for example, in a study on the value of music education on students' academic success, a researcher could sample a group of students from a school, determine which students took music and which didn't, and then examine their grades to see if there's a difference between the musicians and the non-musicians. So this is a hands-off approach. We're just observing two different groups of students and learning about them. Students were not forced to play an instrument. That'd be a hands-on approach, nor not to play an instrument. And the researcher did not tell students to play an instrument one semester and refrain the next. So this is a completely hands-off approach. We're just observing, gathering data, and making conclusions. These features in this non-example right here that I just read would make the study experimental, and we'll discuss that later. Let's talk about a few specific types of observational studies. A retrospective study is an observational study in which data are drawn from past records rather than drawn from a real-time study. So, for example, if you see there's an association between music performance and academic success, students could be asked about their involvement in school music productions over the last 3 years, and their grades from those years could be pulled from RenWeb or whatever data-keeping software the school would use. In a prospective study, and this is sometimes called a longitudinal study, subjects are identified in advance and data are collected as events unfold over time. For example, if we see there's an association between music performance and academic success, or if we want to see that relationship exists, 10 students who play music and 10 students who don't play music could be studied over the course of junior high and high school. Their grades could be sampled from each successive school year as they progress. All right, so you have retrospective and prospective studies. So here's an example from our textbook. In early 2007, a larger than usual number of cats and dogs developed kidney failure. Many died. Initially, the researchers didn't know why, so they used an observational study to investigate. Here's the question. Suppose you were called to plan on a study seeking the cause of this problem. Would you design your study to be retrospective or prospective? And explain why. And I could kind of go either way, but judging by the answer the book gives, I'm going to give you a little hint. Both could yield good results. Fair enough. But which would be more efficient considering the possible evidence you already have? Keep in mind that kidney disease remained rare during the spike in cases. So though there was an increase in cases and it was noticeable, kidney disease was still rare. So considering that, think about whether you'd want to use a retrospective study or a prospective study. All right, hopefully you've given it some thought. If you need some more time, pause the video. If not, let's continue. So the book answers, I would use a retrospective observational study. Even though the incidence of the disease was higher than usual, it was still rare. Okay? Surveying all pets would have been impractical. Instead, it makes sense to locate some who were sick and ask about their diets, exposure to toxins, and other possible causes. So we're looking at information we already have. This is a rare thing, and we already have information about dogs who cats and dogs who suffered this kidney disease. So why not use that as opposed to finding all sorts of new information? If we already have old information, it is often best to use that. So here's what observational studies cannot do. And this might be the most important thing to note about observational studies. An observational study can show an association between variables, but it cannot be used to show causation. Okay? You cannot show cause and effect with an observational study. You can say that variables are related, but you cannot say why definitively. So, Just to be totally clear, an observational study can never be used to show causation. You cannot show cause and effect with observational studies. You cannot show that any variables directly influenced any other variables. Okay, we can only show that variables are associated. Why? We cannot say for certain. For example, if the study from the prior slide showed an association between music performance and academic success, do we know which affected which? Did academic success actually affect music performance, or is there something else in play? Is there some lurking variable behind the association? Now, what is a lurking variable again? A lurking variable is a variable that we are not observing, but that is linking two variables that we are studying to make it look like there's a cause and effect, even though we cannot prove there is a cause and effect. That's what a lurking variable does. We're not studying it, but it links two variables we are studying. So an association is less about the variables music performance and academic success if there is a lurking variable. So what might a lurking variable be that explains the association between music performance and academic success? Well, there could be several things. There could be some students who have just a higher educational acumen, tend to perform better in music. It also could be related to money. Students who come from a wealthier family might have more opportunities. And if you're able to afford an instrument, perhaps you're also able to afford a tutor when academics get tough. So money could be another lurking variable as well. So now we're going to talk about matching for observational studies. Matching is one of the themes of this chapter. Sometimes in a retrospective study or a prospective study, subjects are matched, or they are grouped according to features that are not being studied. And this is a good strategy for observational and for experimental studies. So for example, in a study about the link between music performance and academic success, subjects could be matched in the way that I'm going to describe below, according to their family's economic statuses. For example, we could match a student from a wealthy home that doesn't play an instrument with a student from a wealthy home that does. And then we could match a student from a middle-class home who doesn't play an instrument with another student from a middle-class home who does, and so on and so forth. We could then determine if there is a consistent noticeable difference among the matched pairs. So we're not comparing a bunch of people who don't play an instrument with a bunch of people who do. We are, in this case, taking groups of two, groups of matched pairs, the student from the wealthy home who doesn't play an instrument with a student from the wealthy home who does. See if there's a difference there. Student from a middle class home who doesn't play an instrument with another student from the middle class who does. And we compare those two. And maybe we could have a student from an underprivileged home who doesn't play an instrument with a student from an underprivileged home that does. And we could compare between those groups. And if we find a consistent trend among those groups, we could effectively rule out the possibility that a lurking variable, namely economic status, is distorting the results from the study because we're comparing people of like economic statuses. And now we're going to talk about experimental studies. This is a fundamentally different form of study. Suppose we were slightly maniacal, and we conducted a study that forced one group of third graders to play recorder for a year and forbade another group to play the recorder that year. That would be a little nasty. I would not want to be part of a school that did that. My school certainly does not. But suppose we did. This hands-on approach is a hallmark of experimental studies. An experimental study is a study in which subjects are grouped into control and treatment groups. We will talk very in depth about those. And we have an explanatory variable, in this case, music performance versus no music performance, is altered to determine whether altering the variable influences one or more response variables, in this case, academic success. So, as you can see from that description, an experimental study can do something that an observational study cannot. which is show cause and effect. We can, with an experimental study, show that altering an explanatory variable either does or doesn't affect a response variable. That is the power of an experimental study. Now, this is not to say experimental studies are always preferable. Sometimes experimental studies are just flat out unethical, and we'll talk about that. Sometimes experimental studies don't make as much sense or they're just too inconvenient. But if we can perform an experiment, we can have the chance, if we do it right, of showing cause and effect. So here's the breakdown of an experimental study. We have a treatment group, or multiple treatment groups, and those are groups that do receive special treatment. For example, the group that was forced into music performance is the treatment group in our study. We're trying to show a relationship between music performance and academic success. So the presence of that music performance is the special treatment. On the contrary, a control group is a group of subjects that does not receive special treatment. Oftentimes there's only one control group. Sometimes there are two. There's a control group that has no special treatment, and there is a control group that has a fake special treatment that we call a placebo. It's not an actual treatment, it just looks like one. The group that wasn't forced into music performance is the control group in our study. It's the absence of that special treatment of music performance. And just to be clear, when we list the treatments assigned to each group when describing our study, control, or sometimes placebo if we're using a placebo, we'll talk more about that later, or no treatment, or some other phrase of that nature, is listed among the treatments. Okay, so even though control is the group that doesn't have the special treatment, we do still say control or placebo or something like that to describe the non-treatment. So the two types of variables that we're going to talk about are explanatory and response variables, as I mentioned before. We want to determine if altering the explanatory variable, changing the value of the explanatory variable, affects the response variable in some measurable way. And we're often going to use diagrams like this one to help us understand the layout of an experiment, how we see if a change in that explanatory variable's value affects the response variable. It looks kind of like this. We start with some randomization. We group our subjects into each group, and then we observe a treatment here and a treatment there. This might be a control or a placebo, or something else like that, like a non-treatment. And this could be an actual legit interesting treatment, the treatment that we're going to see whether the presence of it has some kind of effect that's noticeable relative to the non-treatment. And then we compare results and come to conclusions. So now we're going to talk about some more of the nitty-gritty features of an experimental study. So we have at least one variable, and variables are sometimes called factors. So if you see the word factor, that means something very different than it means other places in math. An explanatory variable is called a factor, and we manipulate that explanatory variable, and the specific values the researcher, whether us or someone else, chooses for a factor are called the levels. All right, so right here we have a lot of vocabulary being thrown at us. For example, music performance versus no music performance is the explanatory variable. All right, that's the explanatory variable in our study. Perhaps that variable, that factor, we could say, the factor of music performance versus no music performance, could have three levels, three possible values that that variable could assume. One level would be no practice, and that is the control treatment. That's the non-treatment. You could have a 30-minute of practice per week. That's the next level up. And then the final level, an hour of practice per week. So this is an interesting study. You have no practice. You have 30 minutes of practice, so shorter practice time, and an hour of practice per week, longer practice time. The levels of each factor applied to a particular subject are called the treatments. So when we apply the levels, of a factor, the values that an explanatory variable can assume to subjects, we call those treatments. It's how we treat our subjects. So, for example, we could give one group of students in our study 30 minutes of practice a week. Another may be assigned 60 minutes of practice a week. And then we have a control group with 0 minutes of practice per week. And that would also be listed as a treatment, though it is truly a non-treatment. It's the control group. And then we assign subjects to treatments randomly. We want to use randomness to our advantage. Randomness helps us avoid bias. Human subjects in this context are often called participants. So if you see participants, these are willing participants here. Those are human subjects. For example, lab mice, on the other hand, or bacteria or something that is not human, and the like, are called experimental units. All right. So if we were to do a study on rodent music performance, like we see here, we would refer to these fellas as experimental units. They do not choose to be part of the study, which for some people creates an ethical dilemma. Not so much for bacteria. People really don't care about bacteria. Poor bacteria. At least one response variable is then measured. So this is all about the explanatory variable. We break the values of the explanatory variable or factor into a couple levels. We gather some results about what happens in those different levels of the explanatory variable, and we see if a response variable, in this case would be academic success, changes depending on how much practicing you do in a week. So, for example, we could use average grade for the year. That could be the quantifiable variable for academic success. So we see if all of this up here has some kind of influence, whether we practice 30 minutes, 60 minutes, or 0 minutes at all, has an influence on the average grade for the year, whether a difference in practice time affects your grade. So now let's take it back to this pet food dilemma from the last couple slides ago. In 2007, the deaths of a large number of pet dogs and cats were ultimately traced to contamination of some brands of pet food. The manufacturer now claims that the food is safe, but before it can be released, you got to test it again because we don't want sick cats and dogs. So here's the question. In an experiment to test whether food is now safe for dogs to eat, here's a little footnote about that, what would the treatments be and what would be the response variable? Take a moment, think about it, and then answer the question and unpause the video to check your answer. All right, I'll assume we're ready to continue. Here's the answer. So the treatments could be ordinary sized portions of 2 dog foods. The one from the company, we could call that the test food, and the one that I was certain was safe, perhaps prepared in my kitchen. Well, one of the writers of the textbook seems to think that they're experts in making dog food. More power to them. Or made in a laboratory. The response variable would be the veterinarian's assessment of the health of the test animals. So here we see this test food here. This is the food from the company that we're trying to see if it's still contaminated or not. This test food here would be the treatment that we would give to the treatment group. All right, the group of dogs that eats this food would be the treatment group. Then there's a food that we are certain is safe, and the safe food is the control treatment, and that would be given to the control group of dogs. So the group of dogs that eats this would be the treatment group. And the group that eats the safe food would be the control group. Okay. And then our response variable, hopefully quantitative, would be a veterinarian assessment of the health of the test animals.